All right. So basically, we'll be discussing data representation today, and data representation is just basically an overview of the different kinds of storage methods that we use. These are basically different forms of storage. So the idea is that there are three different forms of data representation, which is essentially binary, decimal, and hexadecimal. Now, if you don't know what something represented in base something means, so we'll go over that even like in some time. But the main distinction between these different forms of data representation is that they use a different kind of base. All right, and generally whenever we write the base of a number, it is written as a subscript. So say this number 1224 is in base 10, 101 is in base 2. So, and if there is no subscript, then it's assumed to be in base 10. All right, moving on. So let's discuss what the idea of having a base means, and let's just begin it with decimal, because it's something that we have used, ever since we started counting. It's the most common form of, data representation, especially considering that we use it in every mathematical operation. So the idea is that the base of your number system essentially is 10. So every time you add a new digit, you increase the entire number by a factor of 10. So that essentially means is that over here you have 10 to the power 0. The next digit you have 10 to the power 1. Next digit 10 to the power 2, and so on. So that's the general idea, that your base is being raised to a particular power, and that power increases as you keep on adding more digits. So essentially your base, it decides how fast you scale. All right, what that essentially means is, say you have 1 and then you have 10, so that scales by a factor of 10, and then you have 100, say. So again, there's a repeated scaling by a factor of 10. Also, what you can understand is that every single digit has 10 different possibilities, which is the same as the base. So what this means is that every digit can have numbers from 0 through 9. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 10 different possibilities, and every digit can have any one of these numbers. All right, so assume a counting system now, because this is a very common way to do maths essentially. So what we'll do is we'll use this as an analogy for understanding other base systems. So hopefully we've all learned place value, and we can understand that the place value of a particular digit is essentially that digit multiplied by the power of 10. All right, that's how we've already learned it. So that's the general idea of place value. And the number of units. All right, so you say consider every every one, like one unit is a particular individual, and just assume that you're counting the number of individuals in a particular group. All right, so essentially the idea is that say 1287 represents a group of individuals or a group of units. All right, I'll refer to them as units, but you can understand. So it represents a group of units. To calculate how many units are there inside of it, what you do is you take the digit and you multiply it by the power of 10. So 7 is the 0th digit or the least valued digit, and you multiply it by 10 to the power 0. You can see that right here. Then you have 8 into 10 to the power 1, which 8 over here and 10 to the power 1 over here. You continue doing that. So essentially you understand that this has 1287 separate units. Now again, this might seem a bit obvious because we've been using this system since forever, but the idea is that when this is applied to base 2 or base 16, you'll get the idea of why we're going over this again. So that's the general idea. You take the digit, you multiply it by the power of your base, and then you get the number of individual units or individuals in that particular group. All right, moving on, binary, which is base 2. So essentially base 2 means that every time you increase a digit, you scale by a factor of 2. So to the power 0, to the 1, to the power 2, so that's 1 over here, 2, 4, 8. So you're increasing by a power of 2. And this is a very, very common form of representing data, because it represents two different states. So also it is used to represent on and off very often. So you can understand 1 is on, 0 is off. It represents only two different states. So again, it has two possibilities, 0 and 1, which is just what I said. So hopefully you can understand the idea that like 10, 2 is the base, all right, and 2 is what is being used to scale. So again, now the idea of why we did the entire place value exercise was to understand that in a binary number like 1010, how many individual units, or in like essentially individuals, does this group contain? Now what you can simply do is 0 into 2 to the power 0, so that's 0, right? You can see that right here. 1 into 2 to the power 1, or this, it's 2. Then you have again 0, so you can just omit that essentially. And then you have 1, which is 2 to the power 3. It's the fourth digit, right? So that's 1 into 2 to the power 3, and that's 8. So that's 10 individuals. So this entire binary number simply represents that there are 10 individual units in this group. Again, this number is in base 10 because that's how we normally count and normally add things up, so it's easier for everyone to understand. But the idea is that this binary number represents 10 individual units. So that is why this entire place value thing helps us understand that exactly what a number is representing. All right, conversion from binary to decimal. This is something that we just saw right now. We saw that if you just take these digits and multiply them with the respective powers of 2, so 1 into 2 to the power 0, 0 into 2 to the power 1, 1 into 2 to the power 2, that's 1 plus 0 plus 4, which is 5. So the idea is 101 in base 2 represents 5 in base 10. Again, this means that this particular binary number represents 5 distinct individual units. All right, hopefully you can get the idea. So it's just a different form of representation for the same way that we have counted. It's just representing it in a slightly different way. Again, so now from decimal to binary, this is probably new. And so the idea is that you repeatedly divide the number you want to convert by 2. So over here in this particular example, I want to convert 13. All right. So 13 divided by 2 is 6, and I get the remainder 1. I take this quotient and make it the dividend for the next iteration, right? 6 by 2 is 3. I get a remainder 0. 3 goes over here. I continuously do this till I get the quotient as 0. All right. Now what I do is I read these remainders from bottom to top, and that is my number. All right. So essentially, I started off with 13 in base 10, and then I get 1101 in base 2. So the idea is 13 equals 1101. So again, this is in base 2. So if you want to check, you can convert it. So this represents 1, this represents 4, and this represents 8. So 8 plus 4 plus 1 is 13. So that works out. But the idea is repeatedly divide a number by 2, keep store of the remainders, and until your quotient is 0, you continue this process and then read the remainders from bottom to top, and you have your binary number. Again, you need to remember that your remainders will always be 0 or 1 because you're dividing it by 2. So it helps you keep an idea and track of that. You have to keep the remainder in mind when you're calculating from decimal to binary. All right, moving on to hexadecimal. Now this is base 16. All right, so it is very useful when you're using it to like store a lot of information. Why? Because it scales really fast. So what I mean by that is essentially, so if you can see over here, see this, this 16 to the power 0 is 1, 16 to the power 1 is 16, and within 5 digits we're already at 65,000. What this essentially means is that every time you add a digit, you're adding a lot of information, because it's scaling by a factor of 16, which is a very, very large number. And although it doesn't seem very large compared to 10, when you're thinking about it on small scales, when it multiplies repeatedly, it works out to be really large, and it becomes larger faster than 10 does. So the idea is it stores a lot of information in a very small space. And again, base 16 scales by a factor of 16. It has 16 different possibilities for every single digit. Now again, in the number system that we normally use, we just have digits from 0 through 9. So for the other 6 digits that we have left over, 10 through 15, we have A through F. All right. It's very, very simple once you get the hang of it. 0 to 9 is just a simple way represented. 10 is represented by A, 11 by B, all the way to 15 by F. All right. Once you get the hang of it, you can just simply convert from 10 to A or A to 10, whatever. That's the general idea. You can convert from the letter to the number. Again, for the place value exercise for hexadecimal, what you can do is consider every unit as one. All right. I mean, one as every individual unit. And what you can see from here is that A10, let's just say this number. So how would we convert it? We'll take 0. It's in the zero, like the place with 16 to the power 0. So just multiply that, you still get 0. Well, you have 1 in 16 to the power 1. So you multiply that, you get 16. And then you have A. All right. Now, A essentially translates to 10. We can see that from here. So 10 into 16 to the power 2 because it's in this position. And that's 2560. All right. So 2560 individual units. Combine all of that, 2576. Now, again, this shows how fast it can scale and how much information it can compact into one single place. What I mean by that is it used 4 digits to represent this particular number in decimal, but only 3 when you're using hexadecimal. And this works, especially more like it's way more prominent when you're using much larger numbers. But the general idea is this, that you can store a lot of information in a smaller space with hexadecimal. All right. So to convert between hexadecimal and decimal, we already saw how from hexadecimal to decimal, we just multiply it with the respective place values. So 16 to the power 0 is 1. So 1 into 1, you get 1. Again, 2 into 16 to the power 1 is 32. And then A again, 10 into 16 to the power 2 is 2560. So, you just add that up and you get your hexadecimal, and you get the number of individual units contained in this particular hexadecimal number, which is basically the way we normally count. So that's essentially the representation in decimal. Now, again, from decimal to hexadecimal, it's very, very similar to binary. The only thing that you're changing is that you're dividing by 16 instead of dividing it by 2. So divide the number, say we started here by 7562. All right. Divided by divided by 16, take your quotient remainder, and quotient goes over here. Repeatedly do that till your quotient is 0. All right. Then what you do is you take your remainders. Now, again, the remainders can be up to 15. All right. Because you're dividing something by 16. So the remainders can range from 0 through 15. So the idea is that whenever your remainder is more than 9, you convert it to its hexadecimal value. So 10 becomes A, 8 stays 8, 13 becomes D, 1 stays 1. And then you read it from bottom to top. All right. So 7562 becomes ID 8A. So hopefully you get the idea. Over here you can see that. Hopefully you get the idea of how to convert from decimal to hexadecimal.